ISTC for today's seminar. This is our final one in our series this semester. We'll begin again in the end of January, and the topic for next semester will focus on water conservation and water use. So I hope we'll see you all here for some of those talks. A reminder that all of our past seminars are archived on our website if you want to view any of those. Today I'm very pleased to introduce our speaker, Dr. Linda Gaines. Dr. Gaines is a systems analyst at the Center for Transportation Research at Argonne National Laboratory. Her primary interest is problem solving applied to efficient use of resources. She began her 30-plus years at Argonne by writing a series of handbooks of energy and materials flow in petroleum refining, organic chemicals, and copper industries that provided background for studies of technical and institutional issues involved in recycling discarded tires, packaging, and other energy-intensive materials. Dr. Gaines has examined the costs and impacts on energy use in the environment of production and recycling of advanced design automobiles, trucks, and trains, and batteries. She has also examined the potential growth of electricity demand by industry and performed technical and economic analysis of alternative fuels, including hydrogen and biofuels. Her most recent work has involved studying ways to reduce petroleum use and other impacts from transportation by recycling of batteries and also recycling or reducing vehicle idling. She holds a bachelor's degree in chemistry and physics from Harvard and a PhD in physics from Columbia. Welcome, Dr. Gaines.
Thank you. Can you hear me? This is on? Excellent. Good afternoon now. Thank you very much for inviting me. And it was a nice drive down. Let me explain to you why we're doing this work. The Department of Energy has been spending a lot of money and effort on developing batteries for vehicles, and in particular lithium-ion batteries. But they wanted to make sure before they actually spent a lot of money and time that they weren't going down an improper garden path. And so the first thing they wanted to do was make sure that they weren't going to be running out of materials. So we did a quick study to check on how much lithium might be needed, and that quickly led to the conclusion that recycling would help mitigate any potential shortages. We have also been doing life cycle analysis of the batteries to make sure that there weren't any significant environmental impacts that were going to crop up. And finally, we have been looking at the recycling technologies from the standpoint of making sure they're safe and environmentally sound, and also to see which ones are most economical, so that once we figure out what the technology is, some business would actually be willing to do it. So to look at the material supply issues, we just answered a set of questions. How many vehicles are there likely to be? How many of them are likely to be electric? Are they likely to be plug-ins or pure electrics? How much lithium would that mean we needed each year? And how much difference would recycling make if you could get the material back? And then we wanted to see whether there were constraints on supplies of any of the materials. So I'm going to go through that extremely quickly because I know the focus is supposed to be on life cycle analysis for this. So we used a market penetration scenario for electric vehicles that was developed for the Department of Energy. This was their maximum electric scenario, and you can see that by 2050, approximately 90% of the vehicles would have some form of electric drive. And that's an extremely aggressive market penetration assumption. But it is, keep in mind, it's a scenario and assumption. There were also other scenarios. One was a maximum penetration of fuel cells. Another was a business as usual. And so this is not necessarily meant to be realistic. It's how much lithium could we possibly imagine that we'd use. Oops.
What are those different?
The dark blue one is plug-in hybrids with a 20-mile all-electric range. The dark dotted one is plug-in hybrids with a 40-mile all-electric range. So that would be equivalent to a Chevy Volt. The light dotted one is just straight hybrids, which are essentially assumed to plateau and then kind of dissipate. From the standpoint of lithium demand, they're the ones that wouldn't use much lithium anyway. And then the solid purple line is pure electrics. So then we actually, in collaboration with the Chemical and Engineering Sciences Division at Argonne, we designed a set of batteries for these vehicles and looked at 4 different chemistries that are shown on this slide. They all have lithium in the cathode. The titanate also has lithium in the anode, and there's also some lithium in the electrolyte for all of them. So from these detailed designs, we estimated how much lithium would be needed per vehicle for each of the battery chemistries, and also the different ranges. And you can see that for the just for a low-range hybrid, you could use as little as 0.2 kilograms of lithium per vehicle. Or if you wanted a vehicle with a 100-mile range using a lithium titanate anode for the battery, you would use as much as 13 kilograms per vehicle. But, let's see, I'm not sure I have that slide. But for that would be a 500-kilogram total mass battery, which is unlikely to be an acceptable alternative. So from that, I infer not that we won't use lithium titanate anodes, but that they won't be used for pure electrics. They would be used for vehicles with shorter ranges. I want to say a little bit about what you do with the material. Once you've taken this vehicle and you've used it, you've got a battery that's no longer suitable for use in the vehicle. It could be used for storage in a utility, and that's been discussed at great length by a lot of people. But even after that, when it's no longer suitable to be used by the utility, the material is still going to be available for recycling, but it may be delayed 5 or 10 years by that. You can also think of various schemes for refurbishing the batteries, but in any case, eventually the material should be available for recycling. And you can see from this graph, which I'll explain in a sec, that that if you can reuse the material, reuse the battery at the end of its life for the vehicle, that material is available 5 or 10 years later, and so it delays the availability for recycling of the material. Now, the top curve there is the total amount of lithium in tons that we could be using cumulatively during this period. No, it's over time, actually. And what I've done then in the curve that comes out brown on the screen is just lagged that curve 10 years and said, okay, supposing you could get all this material back in 10 years, and that then gives you the lower of the dotted curves, and that's the net virgin material that you would need if you used all of the lithium you needed, but then recycled it all after 10 years. And so you can see that because the demand curve is actually turning over, the net demand actually peaks and then starts going down after that. The other dotted line, the higher one, is what happens if that material comes back 5 or 10, I think it was 5 years later. So, come on. Hello. Okay. We also, so that previous graph was U.S. demand and lithium, and what the lithium net demand would look like if you could recycle. We also did a similar thing for world demand. We got a scenario from the International Energy Agency, which was extremely aggressive about EV penetration. They essentially, in one of their, it's blue something, I can't remember the name of it, scenarios, they assumed that, first of all, that all electricity was supplied with no CO2, which is optimistic at best, but that they also assumed that there would be a net 80% reduction in CO2 from vehicles, essentially caused by electrification of vehicles. And so, as you might imagine, they had very, very aggressive penetration of electric vehicles. If you calculate lithium demand based on that scenario, you get the extremely high demand in the top dotted line. Okay, so that's the three graphs for maximum conceivable world demand. So if you then compare that under the three scenarios, the cumulative amount that would be demanded is about 6 million tons under the don't bother to recycle and use big batteries scenario. And that's still much smaller than even what the USGS calls their reserves, which is economically recoverable material. And if you compare that, if you then assume that you can use smaller batteries and recycle them, you get way under even the most pessimistic current view of what world reserves are. So we're not going to run out of the material. You could question whether current production capacity can keep up the pace, but I've got some backup slides, which I won't bother to show, that basically show that current lithium production is something like 60% of world production capacity, and the major producers have enough spare capacity that they're in the process of building that will take us out well past 2020. So in spite of the fact that there are lots and lots of small companies that are rushing in to produce lithium so we don't run out, they're likely to go out of business before we need any of their product. On the other hand, if you look at cobalt and nickel, this is just potential U.S. use of these materials. If we kept using cobalt as the main cathode active material, we would be in danger of seriously straining world cobalt supplies. And that's kind of reflected in the price of cobalt now, and it's one of the reasons why most of the battery manufacturers are moving to other chemistries. So now it gets to the life cycle analysis. So the bottom line is that we're not running out of lithium, but we could get short of other stuff. So most of you presumably know what life cycle analysis is. I stole this graph from somebody in Europe who apparently had stolen it from somebody else, so I have no idea what the original source is. But it gives you the idea that you're starting from the material in the ground and looking at all of the things that happen to this material over the course of its life until you're done with it entirely. And you want to know all of the energy inputs, all of the material inputs, and all of the things that come out as well, whether they're emissions or useful products or co-products. And this is my sort of little LCA soapbox. There's a lot of effort in Europe in particular to come out with a single number at the end of a life cycle analysis. So there's one computer company that actually, when they're purchasing products for their offices, gives them a single ranking. And so you want to buy a product that has a ranking of 5 instead of a product that has a ranking of 4. But this is a summation of a whole set of unrelated factors, and I don't believe that there's really any appropriate and correct way to weight them. I actually tried to do this myself a long time ago and figured out that it was extremely difficult and risky. In particular, if you think about, if you're just talking about the impacts now, it's difficult enough, because do you really want to compare health effects of miners in one country to eutrophication of lakes somewhere else, to environmental impacts in some other place, and how do you add those up and how do you weight them? But more than that, if you start looking at a time dependence and start thinking about intergenerational effects, it's a huge bag of worms, because you don't necessarily want to discount future health effects. You don't want to leave dangerous things lying around for your great-grandchildren. But on the other hand, if you give those significant weight, then maybe you're short-shrifting impacts that are happening now. So I don't really think there's any good way to do it. And I tend to leave impacts separated by impact categories. Okay, this is a sort of generic battery production flow chart that was put together by the EPA, actually, or for the EPA. There's a life cycle analysis of EV batteries that's being done by the EPA because it's possible that some of the anode materials will be nanomaterials. They'll be carbon nanotubes. And so they're doing an entire battery life cycle analysis, including the life cycle of the vehicle, in order to understand whether the nanoparticles are going to matter. And my personal opinion was that they should have just looked at the nanoparticles, but we were happy to see them look at everything else too, because it was kind of a freebie that we could see what they came up with. But you'll notice that there's not much on the back end. It gets to metal recovery, but not really much else, and the material doesn't feed back in. So when we were looking at battery life cycle analysis, the first thing we noticed was we didn't have to look at everything. You don't have to start from scratch if you already know about aluminum and copper and steel, and these make up a significant fraction of the mass of a battery. So those are materials that we already know about, and they're already in the big database that we use, which is part of the GREET model. And I assume that somebody's talked about that a little bit already. But it's greenhouse gases, regulated energy and emissions in transportation or something like that model. And what it is essentially is a very large two-part spreadsheet. GREET 1 has to do with the fuel cycle, so it's digging out the coal and beneficiating it and transporting it to a power plant and burning it and looking at the emissions. It goes from fuels in the ground to when you would use them in your vehicle. And the other part of it is GREET 2, which is the vehicle cycle, and that has to do with producing the vehicles that will use those fuels. And obviously, if you're looking at the battery production and then recycling, it's part of the vehicle cycle. So we have been using those materials that are already in there and trying to get information in some detail about the battery-specific materials. And the thing that's really interesting about that, or challenging, maybe you could say, is that in some cases there is a small number of companies that are producing them, and in many cases the information is proprietary. And so we've had to be imaginative in some cases in estimating what the energy use is for these things. But we've got some preliminary results. This is for the battery production itself. The left side is in joules per kilometer, not my choice. And you can see that the little dark bar at the top is the impact from the battery production for a PHEV 20. So this is a vehicle with a fairly small battery. If you wanted an electric vehicle with a 200-mile all-electric range, that slice would be on the order of a factor of 10 larger, but it still wouldn't really compare to the fuel cycle emissions, which are really the energy use that it takes to produce the fuel and fuel your vehicle, whether it's with electricity or with gasoline. And I believe that particular chart is made with sort of an average estimated mix that somebody with a PHEV 20 might be using over the course of the vehicle's life. The right side is just the energy to make the battery. And the reason that we've got that in here in particular is we had some older estimates for nickel metal hydride batteries that showed that the actual manufacturing stage where you fabricated the battery materials and coated the substrates and rolled the battery and tested them was actually fairly energy intensive. And what this graph shows is that it's not so energy intensive, which to me means that when you're recycling the materials, you can really get back a large fraction of this energy. And what the headline on that one points out and reminds me to tell you is that even though something like only 2% of the energy to produce for the vehicle's entire life cycle is for production of the battery, it does account for something like 20% of the life cycle SO2. And the reason for that is when you take copper and cobalt and nickel out of the ground and smelt the ores, there's a huge amount of sulfur dioxide that's released. And even if you've got well over 90% capture of this, there's still a very significant amount that's released to the atmosphere. So this is a place where recycling actually does significantly reduce an environmental impact. Well, so we've shown that reducing the life cycle energy use for the vehicle, and by the same token CO2, is not the major reason for recycling the vehicle and recycling the battery. But we have shown that you can alleviate potential materials scarcities by recycling. It's possible that the recycled materials will be cheaper, although not necessarily. And you do reduce any impacts that you had from the production. And what turns out to be the real stick here is that in many places, especially in Europe, and I believe there's some regulations in California coming as well, battery recycling is required. So that means that even if it doesn't pay and even if it doesn't save you a lot of energy, you've got to do it. So what should you do? Well, you can recycle materials to all different parts of a production process. You can take it all the way back and pretend it's like an ore and start from scratch. Or you can, if you're really lucky, take the pieces out and reuse them in a battery. So we've been comparing battery recycling processes to figure out which ones are the best. And criteria that we are thinking about are energy use and emissions, and which ones actually get back the most materials that could be in tight supply, what the economics look like, which is really important, whether the things are allowed by regulations. So, for instance, some of the processes may not satisfy all of the requirements of the European battery take-back laws. And other various factors come into it as well, as you'll see. So here's a quick slide that I've made recently that's approximate numbers, and it gives you an idea of why it matters which cathode material you're using. Some of the cathode materials are listed on the left there, and you can see that the constituent elements, if you've got cobalt in the cathode, are pretty valuable. And in fact, the constituent elements aren't worth a whole lot less than the cathode material itself. And so you don't much care how you get it back, as long as you get the cobalt back, and nickel as well. But if you've got a newer chemistry, like the lithium iron phosphate, the constituent materials are pretty much worthless. And so if you want to get any economic incentive for doing this recycling process, you hope you can get cathode material back, or maybe something else that's valuable, which we haven't quite figured out yet. And in Europe, because you do have to bring the batteries back, the previous slide was just really talking about the cell materials, but the entire battery pack has a lot of other stuff on it as well. It's got electronics and electrical conductors and a big housing. And so those materials may actually help the economics, because those are materials that you've got to bring back anyway, and they will have some value as well. So now I'm going to go through quickly the three types of battery recycling processes that are actually in advanced enough stages of development so that we can actually characterize them at all. The one that's commercial on a large scale, and the plant I visited is actually in Belgium, is just smelting. And that essentially means you've got a big furnace that's running at high temperature, and you take the entire battery, you don't even have to chop it up, throw it in, and the organics are burned. The carbon in the anode acts as a reductant. You get nickel and cobalt and manganese out the bottom, and the lithium goes to the slag, as does the aluminum. And that slag right now is used as an additive for cement manufacture. And the people who are running these processes will tell you at great length how much it improves the property of the cement, but it's still a pretty low value product to be getting out. Okay, and this is a flow chart that we've made of this particular smelting process in Belgium. Note that lithium-ion and nickel metal hydride batteries are going in. This is for their existing plant. They've just opened a new smelter at the same location, and they're going to be running batches of one battery type at a time there. So instead of getting a mixed cobalt nickel product out, we'll be getting just a nickel product out from the nickel metal hydride. And that will reduce the energy for the refining, which is actually not shown on this. So we're going to need to add that when we do the LCA, because the LCA is going to compare virgin battery material production and finished battery production to production using recycled materials to see what the actual benefits are. And then, excuse me a second. As I mentioned, batteries are collected in Europe, and there are two pictures there that show how they're collected in Finland. One is just at a Radio Shack kind of store where batteries are dropped off, and the other is in the Helsinki airport, where if you happen to be going through the airport and have dead batteries, you can throw in the battery recycling. In the lower right is the battery storage in just barrels, which makes me a little nervous, at a plant in the middle of Finland. I'm 200 miles from the next biggest city, which is 20,000 people. So it's really in the middle of Finland.
None of the slides show that the battery terminals need to be taped.
And in fact, they don't seem to bother so much in Europe. That's a real concern, and that was why I mentioned about the storage, because you would want them to be stored either in sand or, as talks goes in Trail, British Columbia, in berms or bunkers, so that if there's any potential problem, because if you're going to be storing a large number of spent batteries, you might have a fire sometime. So yeah, that's why I'm concerned about this particular plant. At that plant, what they do is they sort the batteries essentially by hand, and the lower left picture there is some lithium-ion batteries that they've gotten in. And then they chop them up, basically with no other treatment, and they get little bags. Well, they get large quantities of this black flake material that's essentially everything that was inside the battery and the casing as well. And they're sending that material to a cobalt recovery plant in Kokkola, Finland, where they leach the cobalt and the copper out. And again, the lithium is lost, but it's not much lithium because the plant is actually having as its primary feedstock material from that big tailings plant in the Congo. And so the lithium-ion battery material is only a very small part of that plant's input. So it's not much lithium on a percentage basis of their whole feed.
So they haul those tailings from the Congo to Finland?
Yeah. 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 They put them on, big ships of some sort. Yeah, and Kokkola is a coastal city, so they don't have to ship it overland at all. But yeah, it's. I thought that was pretty cool. This is a generic flow chart for battery production, and at the top, it's all very general terms and not specific to battery chemistry really at all. But the point is that at the top you've got raw materials that come out of the ground or out of a salt lake. And at the bottom you've got finished cells. And for each of the different trains of materials, there's a set of blue processes that you go through in order to get to a finished battery. And for the smelting processes or the leaching processes, the processes that you replace by doing the recycling are just the ones that are in that shaded oval. So it's just the production of the ore and primary metal production. And so you've just displaced a small fraction of the processes. Now, if you listen to the people who do this, they will very proudly and appropriately tell you that they've saved 70% of the energy that it took to make those primary metals. But they haven't done anything for the lithium or the electrolyte or for the carbon. Now, the smelting processes are running economically because of the cobalt in the feedstock. What happens if you use some other battery chemistry, which is what the automotive companies are starting to do? Well, the smelters aren't real happy about that, and they are urging people to keep using cobalt because it's their, it gets them large profits at the end. Any nickel comes back out, and they can recover the nickel, but there's a whole set of some of other materials that just go to the slag. And there was actually a conference last week on phosphate materials, and they were very interested in the fact that the phosphates, in fact, end up in the slag, and so those are lost as well. Now, we've been nudging the smelters about possibly recovering materials from their slag, and so they've come up with that flow chart on the bottom to show that they could, in fact, be recovering lithium carbonate. And they're thinking about doing it, but they notice, rightly so, that that's, in fact, a more complicated and energy-intensive process than it would be to just get the lithium out of brine in the first place. And so they're not currently doing that. On the other hand, if you have nickel metal hydride batteries in, and this is a little aside, as your feedstock, because the market for rare earths is getting tight, let's say, in particular the Chinese are thinking about restricting their exports to the U.S. and other places. There's actually much more interest in recovering the rare earths from the slag. And in particular, Umicore, the company in Belgium, has a deal with a company called Rhodia, which is now recovering the rare earths from the nickel metal hydride battery slag. Now, the next kind of process is a little bit more elegant. It's a lower temperature process, and basically it's hydrometallurgical. And so you don't need as much energy to do this, and you can actually get more materials out than just the basic metals. The Department of Energy awarded a company called Toxco about $10 million under stimulus money to build this plant in Ohio, which is currently under construction. And at that plant, they will start by recovering both nickel and metal hydrides from nickel metal hydride batteries, but they hope to be actually recovering cathode material. That they're not quite sure how yet, though. Their current process in Trail, British Columbia, recovers the lithium carbonate. And this just shows some process pictures from that. And again, a flow chart. And the important thing to notice on this is that the lithium is, in fact, recovered. And so going back to that same generic flow chart, you start displacing a larger number of processes, and you've done it with a lower energy process than smelting. So this is when we actually get the LCA completed, this is going to look a little bit better. But again, what if you use a different cathode material? And I can't really answer that yet. I have some chemists thinking about it, and in fact, the people at Toxco aren't quite sure what they're going to do yet. They hope they'll be able to get cathode material, but they're going to start just by recovering the the metal hydrides and the nickel from the nickel metal hydride batteries, because that's really what the major stream that's coming back now has in it. So this one still has some work to be done. And then we get to the last type of process, which is, I would call, just physical processes. And this is not a commercial process yet. It's been demonstrated basically on a bench scale. And what the companies that has done this has done is taken batteries and crushed them enough so that the casing was breached, used supercritical CO2 to extract the electrolyte, including the salts in it. That material can, in fact, be recovered and reused. They then take the rest of the material, chop it up, and use a series of physical processes, including froth flotation and gravity separation, to separate cathode material and anode material and the aluminum and the copper from the substrates. The aluminum and the copper can get sent to secondary metal processing, and they have actually demonstrated that they can make new lithium-ion batteries with the materials that they recover. The cathode material may need to have some additional lithium added to relithiate it, but they do in fact get batteries with apparently good processes, good properties. Again, this is a low energy process, and it has a big advantage in that it can be run on small scale, so that if you were Dow or A123 and had your manufacturing plant and had manufacturing scrap coming out the back, you could put in a process like this and actually recycle your own waste materials. One thing that I should mention is if you want to get out good quality product, it helps to have a separated and pure stream going in. And so if you had post-consumer batteries, you might have to separate them, or else worry about how to deal with a mixed cathode stream at the end. But again, if you're a battery manufacturer now, that's not a problem. The other potential problem with this is this material is not coming back for 10 or 15 years. I don't know that in 10 or 15 years batteries will be using the same cathode materials that they're using now. Is the material that comes back going to be a dinosaur? Is it going to be saleable? Is there some other valuable material that you could get out? And that's one of the questions that we're actually asking right now. And this is some examples from one of the other researchers at Argonne over in the Chemical and Engineering Sciences division. His name is Dan Abraham, and he's actually taken some used batteries apart and done detailed measurements of various types and looked at the crystal structure of the active materials before and after use. And you can see this is some anode material that is virgin at the top and used at the bottom. And what you see on it is a coating, essentially. It's the SEI layer. And there's some question as to whether having a large SEI layer is going to impact on the performance if you try to use this material again. It's also possible that the material can be cleaned and used again. So there are questions about this that are still in the process of being answered. So there may be some limit to how many times you can reuse the material. But if you can reuse cathode material and anode material, you can displace just about all of the pieces of the battery with recycled materials, with the exception of the separator, which is a thin plastic layer that goes between the electrodes, and it's polyethylene or polypropylene that's been stretched in such a way that it's got very specific porosity properties. And when you would recover it from a process like this, you'd get small pieces, and it would be suitable for reuse as a polyethylene pellet, but would have lost its great extra value for that it had because of its thin form. Again, what happens if you use some other cathode? And in this case, I don't think it's a problem at all. They have in fact gotten some funding to do the same thing with manganese spinel cathodes, and they've also demonstrated the same process with nickel metal hydride batteries. So except for the fact that you want to have a separated stream, I think this process would work for just about any battery chemistry you put into it. You might have to use a different set of solvents or liquids in your gravity separation or whatever, but the basic idea should be the same. If we get to other battery chemistries like lithium-air, I have no clue. It's so far down the line that people haven't even made the batteries, so I don't know how people will recycle those. So this slide actually summarizes the differences of the battery recycling processes. And the key points are that if you smelt it, you're not going to get much out of any value if you've got one of the non-cobalt containing chemistries. And on the other hand, the physical processes would require a fairly pure input, and there is some question about whether the product will be valuable when it's coming back in 10 or 15 years. And so finally, I just want to mention one thing. I mentioned that the separator is likely not to be recoverable per se, but you can get the plastic back, and there's somebody at Argonne who's actually demonstrated a process where he can take used plastic bags, and presumably he could do the same for battery separators, and make them into carbon nanotubes. So that would be an example of upcycling, where you take some waste product and make it into something that's more valuable than the material you had to begin with. So I think that's kind of cool. And very last thing is almost any of these recycling strategies would benefit from a set of sort of logistics things. If you could standardize the materials, you wouldn't have to worry about separating them. If all of the batteries were the same size and shape, then maybe you could design a machine that would take them apart for you. And lacking that, at least if you can label them, you know which is which, and you know which process to send them to, or you can separate them for batch processing in the same process. And I'm actually a member of an SAE working group that's looking at recycling issues in particular, and we've got a draft document about labeling of the batteries, which if anybody's interested in, you are welcome to review. And with that, I will say thank you. That's a picture of a volt battery, actually. And you can see that it's not just the cells. So does anybody have any questions?
Yeah. Where is most of the lithium?
Right now, most of it comes from salars, which are salt lakes in Chile. Argentina also has a lot. Bolivia has the largest reserve in the world, but they actually haven't managed to exploit it yet for technical and political reasons, I think. The U.S. also has some lithium, and we used to produce our own before they figured out that they could get it really cheap from the salars in South America. There's also some salars in China, and China is producing its own lithium. There's also some lithium in Finland, and there's some in Afghanistan, which I thought was rather amusing when that news came out. I just can't imagine that we would go into some big economic venture in Afghanistan at this point. And then it's even sillier than that because the Japanese are thinking about getting lithium out of seawater, and I don't think they're going to need to do that for quite a while.
Any other questions? I have a couple of questions. One is lithium. Isn't lithium also used for like medicines?
Mm-hmm. Very small quantities, but
Very
yes.
small. Okay. Another question is you mentioned using supercritical
CO2 to extract.
I'm not a chemist, so how does supercritical CO2 play a role in extraction?
The material dissolves in it, and you can pull it out. I'm not a chemist at that level either, but apparently it works.
High temperature pressure.
Well, it's not very high temperature, though.
Oh, for CO2.
Yeah.
I'm thinking of water, but it's
Yeah.
high pressure.
Right, no,
1500
it's
PSI.
relatively high pressure, but it's actually cold, I think.
And the CO2 is pressurized, so it acts like a solvent, and then it leaches out the material.
And then you have no solvent all the time. So it's
Which makes the battery inactive so that you don't have to worry about fire.
2000.
Thank you.
Question, it seems like the thing that you're saying is that the physical processes are going to be ultimately what needs to be gone to. But
That's my personal opinion.
That's your, yeah, it seems to make sense for everything you said. But it seems like smelting for the near term is the way that things, of course, are the
Well, it's already happening.
yeah.
And in fact, Tesla makes those cars out of the little electronics batteries, which is, they have 5,000 little 18650s in a Tesla. It's kind of funny. But they actually have demonstrated that you could recycle batteries with Toxco, the one that actually can get the lithium carbonate back. But
That's process or just
that's hydrometallurgical.
Okay.
But they've now signed a contract, at least in Europe, to have their batteries go to Umicore so that they're going to go into a smelter. Because that's the process that's commercial right now, because it pays because you get the cobalt back.
I know this wasn't the subject talk, but you start saying organics burn off, and I imagine that there's a lot of toxic stuff that comes out.
They actually have a high temperature furnace or whatever at the back end, so that anything that might be bad is burned off.
So smelting can be technically done cleanly.
Yeah, it is pretty clean actually.
You have one in your backyard.
No, but I visited the plant and didn't smell anything bad, and they do comply with all of the European air regulations, and the company is actually pretty conscientious and trying very hard to be as green as they can. I mean, to the extent of like having green roofs and.
When a battery performance is degraded by use, is the degradation a chemical or a physical process?
That's a really good question, and I would refer you to Dan Abraham at Argonne, first of all, because I've seen his slides, and you can look at the crystals from very close, and some of them have cracks in them, and some of them have things coated on them.
So it seems to be a physical process. And
pretty
so
much, but
it seems to me then that when you recycle, you shouldn't have to go through all this chemical processing. All you have to do is go through the physical process.
Well, but
to get it in the proper form again.
Well, it depends. Supposing you've got some crystal that's this big and that's the optimum size for battery performance, and because of previous use, the crystal is split into smaller pieces. I'm not sure how you get it back to being a big...
Well, you got it there in the first place, you must be able to get it back.
Yeah, and that I was saying that in the direct recycling process, they actually are relithiating, so they're putting in some more lithium, but they're treating it at a lower temperature than you needed to make the battery in the first place. So yeah, the idea that you've got to split the molecules apart to me is less elegant, and if you can reuse it the way you made it in valuable form, there's something very attractive about that. But you do have to ask whether when you get it back, anybody's going to want it. If you're talking about electronics batteries, they come back in 2 years, 3 years, something. And so the chemistry is likely still to be used. But if you've got an automotive battery that's been used in a car for 10 years and then been used to store grid power for 5 or 10 years, you're talking 15 or 20 years from now. You think the same cathode materials are going to be used? I don't know.
Suggests you should have batteries designed with replaceable components.
Ooh.
So you just drive in and get a new set of plates, like filling your gas tank. And then those plates are recycled, so the turnaround time is a month, not 10 years.
Except that what we're talking about, even for the automotive batteries, is cells kind of that size, with
Yeah, I
a
know they're
whole
designed
coil.
that way now, but they might
Oh,
be designed differently. If you redesign for this kind of replaceable component.
You are welcome to try to do that.
Well, I mean,
No, it's a good idea, in theory. And obviously, you could do that with lead acid batteries.
Was there any other questions? Okay, I just had a couple. One is, what do you see as the main data gaps in doing LCA analysis for these kind of batteries? And so-
Basically, anything that is done by a very small number of companies that are worried about proprietary information.
The other question I had was, what happens to lithium-ion batteries in the U.S. now on carbide? What's sort of the...
Carbide, you mean
Yeah.
the lead acid batteries are recycled almost completely. In the U.S., yeah, and that's really sort of the poster child for battery recycling, because you go and you get a new battery, your old battery goes back. In fact, in the U.S., goes back on the same truck that brought the new one to the company, and they can chop. East Penn in Pennsylvania chops up the polyethylene case and makes a new case. They resmelt the lead and make new lead plates. They can even recycle the acid. So they're doing, sort of the best you could imagine doing. Now, one interesting point that I just found out is that in Europe, you can't send it back on the same truck because there are transportation regs against that. So you end up, when you're looking at this, especially internationally, you get all kinds of little glitches that have to do with local laws, and it makes it fun.
Any more questions?
I got one quickie. What with NiCad and lithium? Why is it that the lithium you can put it in a smaller package versus the NiCad and it lasts longer? Is that correct?
Yeah, it has to do with the chemistry and the energy density of the material, and you've asked the wrong person.
Okay. Now, what about battery memory? Does the lithium
Yeah,
have
no.
memory? Like NiCad does have
Right.
memory.
Yeah, that's one of the big advantages of lithium-ion batteries.
Okay,
But the main thing is that they're smaller and lighter,
Okay.
get much higher energy density.
And I know if you reverse the polarity on the NiCad, you can erase the memory and pretty much recharge the battery. Have you ever heard of that?
Ask a battery expert.
Okay, thank you very much.
Thank you.